The design of an interface for an embedded system is often a significant project in itself. Understanding basic methodologies for interface design help us deliver complex interfaces that actually work.
Different types of applications place different demands on the embedded system and on the interface. For example, audio rate signal processing often requires high CPU performance, in part because it needs a high sample rate to provide high quality audio. Any network connection often uses medium amounts of bandwidth. A closed loop control system often requires medium to high CPU performance and a medium to high sample rate, perhaps somewhat lower than high quality audio, but depending on the application, perhaps at that rate. Network bandwidth is often lower. Event processing is designed for infrequent operations, so CPU performance required is often low, low sample rate, and low network bandwidth. Several types of requirements shape the nature of the interface. The sample rate determines how much information is in the digital signal. Analog signals that have higher frequency content will require higher sample rates. Numerical precision and dynamic range determine the accuracy of the digital computations that we perform on this digitized signal. Latency, the time from input to output, is a critical parameter in any sort of closed-loop system. Manufacturing cost and design effort are factors in almost every design, and they are important constraints on the overall design process. This generic block diagram helps us understand the role the different parts of the system play. The CPU and the bus form the core of the embedded system. The interface uses two types of registers, data and status, to communicate to the processor through the bus, and a mode state machine helps control the interactions of the interface with the bus and the CPU. Digital and analog circuits deal with the signals that come with or go to the physical plant. The simplest form of the mode state machine that interfaces between the rest of the circuitry and the bus looks something like this. The interface sits idle until it's told it has something to do. Then it performs its processing, and when it's finished, it goes back to the idle state.
The choice of a microcontroller or computing platform is an important part of the interface design process. Considerations include both hardware and software.
The hardware platform includes processor or processors, the bus interface, the I/O devices, and the software development environment. The software part of the platform includes what goes by any of several names: BIOS, hardware abstraction layer, or board support package, the device drivers, and the executive or the operating system that control the tasks. We can evaluate processors with several different metrics. Performance has several different meanings. Throughput means the rate at which we finish executing instructions. Latency is the time from when we start executing an instruction to when it finishes. Both are important. Latency is particularly important in closed-loop applications. Interrupt latency is the time it takes for the CPU to respond to the interrupt. That is a very important consideration in lots of interactive systems. Arithmetic precision determines the precision with which we perform. Arithmetic precision determines the accuracy with which we perform calculations. Bus performance limits how quickly we can talk to devices, and therefore also limits how many devices we can put on the system. Utilization is a basic metric of how efficiently we use the processor. It's the fraction of the CPU time that is actually used for computation over a given interval. We can look at a layer diagram to better understand the organization of an embedded system. The hardware is at the bottom. That includes the processor, the bus, and ultimately the interfaces. A hardware abstraction layer that provides a few basic drivers, and then we have additional drivers that are specific to our own project. The hardware abstraction layer is known in the PC world as a BIOS. It may also be known as a board support package. An executive manages the sets of tasks that actually perform the application. The executive ensures that the CPU is allocated properly and that tasks get the time they need in order to perform their functions.
Real-time systems are typically structured as sets of tasks. The task execution is controlled by a real-time executive, which in turn is executed under the control of a hardware timer.
This piece of code shows how to build a very simple executive. We have some global variables that allow us to keep track of time. We have an interrupt service routine for the timer that determines when the executive runs. This is the main program, and the while loop represents the executive itself. The executive checks for a flag to see when the next timer interrupt has occurred, and it then performs the tasks that are required by the application. We wait for the flag rather than executing the executive inside the service routine, because running a long piece of code inside the service routine will prevent lower priority interrupts from occurring.
To summarize, embedded system interfacing combines mixed signal analog and digital design along with hardware and software design. A set of signals from the physical world is captured using a combination of analog and digital circuits. The data is transferred to the processor via the bus. A software stack controls the execution that delivers the intended function. A real-time executive manages a set of tasks in order to perform the application's desired function.